So, even in our last class we were talking about the field created by different distributions and we completed some, right. So, we completed field created by ring, we completed field created by disk, and we completed field created by infinite sheet. Let us see what we did in the last class. So, we derive the expression for field created by the ring at any point on the axis, right, and the value of electric field came k q x divided by r square plus x square to the power 3 by 2, where q was the charge which was uniformly distributed over ring. Right. So, this is meant for uniform distribution when charge is uniformly distributed, and x here this is x, right. So, this distance is x, at distance x from the center we got this field. The direction of the field was along positive x axis. So, we got field in this direction, this was the direction of field, right. And we talk about the variation of the field, we have seen that this field achieve its maxima at x is equal to r by root 2 and then it reduces further. So, at center it will be 0, at infinity it will be 0, and somewhere at x is equal to r by root 2 it will be maximum, right. Now, then using this result, we derive the result for disk, right. So, integrating this expression for any point on axis, we got sigma upon 2 epsilon naught 1 minus cos alpha, where sigma was surface charge density. So, if charge is distributed over the face of the disk, then the field created by disk will be away from the disk along the axis, and the magnitude of that is given by sigma upon 2 epsilon naught 1 minus cos alpha, where alpha was angle between line joining periphery to that particular point and x axis. So, this was alpha, right. So, this can also be written as x divided by under root x square plus r square, right. It is easy to remember this way, that is why I have converted the whole expression in this format, right. Now, using this result we derive the result for disk. What I said, you can assume that this is a very large disk where r is tending to infinity. If r tends to infinity, if r here tends to infinity, this whole term will turn to 0, and if this whole term becomes 0, then we are left with only sigma upon 2 epsilon naught. So, field due to infinite charge sheet of surface charge density sigma is given by sigma upon 2 epsilon naught. Look at all these three expressions. This contains x, that means field at distance from center x depends on x. Similarly, here field depends on x, but in this situation field is independent of x. Everywhere field will be same. So, if you visualize very large sheet, in front of large sheet everywhere field will be same, and magnitude of that is given by sigma upon 2 epsilon naught. In last class I said that this is called uniform field, and these two are non-uniform fields, right. So, the direction of field in front of sheet will be away from sheet if charge is positive, and it will be towards the sheet if charge is negative, right. So, as I have taken positive charge, field will be in this direction, away from the distribution, right. Same thing happens on other side. If I take point somewhere here, it will be like this. If you take sheet in front of it, field will be in this direction, and in front of it this side, field will be in this direction, right, and magnitude remains same, sigma upon 2 epsilon naught. Apart from these three, we also discuss field produced by arc, circular arc. So if I say take circular arc of radius capital R, then the field at the center of arc was away from distribution like this, and the magnitude is given by 2k lambda r sin phi by 2, where phi is the angle subtended. So total angle subtended is phi, and here we are getting sin phi by 2. Lambda is the linear charge density. Total charge on semicircular arc divided by the length of the arc, r phi. So this is what we have done in the last class. Now let us see what we have in today's session. Spherical shell, field produced by uniformly charged spherical shell. So if charge is uniformly distributed over surface, here I need to define surface charge density. So total charge is Q distributed over surface charge density will be sigma is equal to Q divided by 4 pi capital R square, right. So R is the radius of sphere, spherical shell, total surface area will be 4 pi R square. So charge divided by 4 pi R square will give you surface charge density, right. Now if I ask what is the field at center, somewhere here, it is very easy to predict that here field will be 0. So at center it will be 0, we can easily say. If you take element diametrically opposite, so this element will produce field in this direction, and this element will produce field in this direction, and these two will cancel each other. Similarly, if I take element somewhere here, an element somewhere here, these two elements will produce field in opposite direction and they will cancel each other. So on the surface, if you take diametrically opposite elements, they all will cancel each other in pair. So the net field exactly at center will be 0, right. What about field at any point inside? If I take point somewhere here, what would be the field there? So I just want to generalize the result. So I want to find out what would be the field at this particular point, right. So I can proceed the same way. I will take the element somewhere here, and this element just to make you understand, I am drawing this big diagram, otherwise this is very small element. So this angle and this angle, they are very small, right. So this element and this element both are subtending same solid angle here and here. So the angle subtended by this one will be equal to angle subtended by this one, right. So this angle is same as this angle, right. I hope you understand the concept of solid angle. So solid angle, if I take a spherical part and I join all contour to the center, then angle subtended here is given by solid angle is equal to area of this surface divided by r square, right. So like linear angle if I join all the point like this angle, that is phi is given by length divided by r divided by radius, right. So in case of solid angle, instead of length it becomes the area. So surface area of this part divided by r square will give you solid angle subtended by this surface at that particular point, right. So here the element, because this is 3-dimensional diagram, element will be covering some area here and element will be covering area here. So both the area will be subtending angle at this particular point. I have taken the element in such a way, if I join this one to this one and this one and this one, I am talking about these two charges. Let us call this one as dq1 and this one as dq2, right. So only thing right now we know that the angle subtended by this one and angle subtended by this one at this particular point is same, right, and that we are talking about solid angle, that is area divided by r square. So I will write solid angle formula d area divided by r square. If I take whole sphere, then here I will write 4 pi r square and this is r square, this and this will get cancelled out. That means total angle subtended by sphere at the center will be 4 pi steradian. So this angle unit is radian, this angle unit is steradian, right. Now let us see how to use this. So if I ask what is this charge? This charge is surface charge density into area dA1, sigma is what? Sigma is dq by d area. So if I need dq, that is nothing but sigma into d area, that is what I have written here. Similarly for this charge I can write sigma into dA1, where A1 is the area of that particular patch, right. So area of this patch A1 dA1 and area of this patch is dA2, this is dA2, right. Now net field at this particular point. So as charge here is positive, it will produce field in this direction and charge here will produce field in this direction. That means to get the net I need to subtract. So net field is equal to field produced by first element minus field produced by second element, both are in opposite direction. So I have taken direction into account. Now I have to write, I have taken direction into account, that is why I am subtracting. Now I need to write magnitude. So this magnitude, look at this one, because of small elemental charge, the field at distance r let this distance be r1 and this distance be r2. What we can write? K charge on the element divide by charge on the element divide by separation square r1 square minus K dq2 divide by separation square, right. So, if I substitute the value of dq and dq2 from here, then what I will get is K sigma into dA1 divided by r1 square minus K sigma dA2 divided by r2 square. And look at the definition of solid angle. From solid angle definition, this is the angle subtended by this patch at this point, and this one is the angle subtended by this patch at this point. As both the angles are same, we can take these two terms out. These two terms are same, they will cancel each other. As they will cancel each other, the resultant field because of these two elements at this particular point comes 0. That means these two patches at this general point produce net field 0. If I take patches like this somewhere here, they will produce field 0, here net field 0. Similarly, I can take patch at any point on the surface of the sphere, the resultant is coming 0. That means no matter wherever you take point, the net field inside at every point is 0, right. This is one way of doing. Another way of doing is you can take ring on the surface, and write the field created by ring and integrate from 0 to pi, then you will get the same result 0. But as that is mathematically complicated, I am not following that method. I hope this method is clear, right. So, at every point inside uniformly charged spherical shell, field is 0, right. If distribution become non-uniform, for example, if I assume or if I take the situation where charge this side is more as compared to charge this side. So, obviously when charge this side is more as compared to charge this side, the field at point somewhere here, or you can say center, at center this will produce more field and this will produce less field, the net field will be in that direction. So, this is valid only when charge is uniformly distributed. If charge is non-uniformly distributed, then again taking a ring on the surface and using sigma for the given distribution, we can find out field at any point inside, right. So, I hope what happens inside is clear. Now, let us see what happens outside. So, inside we have derived field is 0. Now, outside. Now, same way for outside point, again at an angle theta, I can take ring with subtend angle d theta, and because of this ring, look at this one, because of this ring, I hope this diagram is clear because it is in 3 dimension, right. Now I have taken element as ring, so charge will be distributed over ring, and because of this element at this particular point, at general point x, you know how to write the expression, right. So formula is k q x divided by x square plus r square to the power 3 by 2, right. This is the field by ring. Now if from here this distance I am assuming x, if from here this distance is x, then I will write x here, right. Or if I am assuming this distance to be something, for example let us take this distance s, instead of defining distance from the center of a ring, if I am assuming this distance to be something r, then from center of ring, if this distance, this is r, towards angle this will be r cos theta, and this remaining distance, this distance which we are writing x, that is nothing but small r minus r cos theta. Small r, x will come small r minus r cos theta, right. So that I will substitute here, right. And the radius of ring, look at this one, this will be radius of ring. If this is r, in front of that this will be r sin theta. So this radius of the ring will be r sin theta. I will substitute in place of this r, which is the radius of ring, r sin theta. This is the field produced by a ring. If I integrate, then I will get the total field. This is one way of doing, right. Another way, another way is using Gauss law, that we will discuss later, right. For time being, you can keep in mind that as distribution is highly symmetric, charge is distributed uniformly over the surface, as distribution is highly symmetric, about all the line you draw, this distribution is symmetric, that is why I am calling it highly symmetric. As the distribution is highly symmetric, I can assume the whole charge is concentrated at center for any point outside the sphere. So to find out the field outside the sphere, I can assume that whole charge is concentrated at center at distance r. If whole charge is concentrated at center, the field is given by E is equal to k, if total charge is q, q divided by r square, right. So inside field is 0, inside field is 0 and outside field is E is equal to kq divided by r square, but keep in mind that this is valid only when distribution is uniform. If distribution become non-uniform, then again the method I told you, take the ring, integrate, you will get the field at that particular point, right. So for uniform distribution you can directly apply this expression. Now, so for outside point I can write at this point P, I can write kq, k is nothing but 1 upon 4 pi epsilon naught, q divided by r square, right. And on surface this small r will be equal to capital R. So this small r can be replaced by this capital R, right. So this is for surface, right. Now if I want to plot the variation as I move from this point from center to the infinity, then how field varies? Inside to everywhere it will be 0, and outside you know that it is inversely proportional to r square. Let us draw the variation. So at every point inside you can see that field is 0. This I am plotting E as a function of distance from center r. So on the surface its magnitude is k q divided by capital R square. Here small r is equal to capital R, and when you cross the surface, here it will be 0, and when you cross the surface, field varies according to E proportional to 1 upon r square, right. So because of shell inside and outside, both the points are clear. Now let us take solid sphere. So solid sphere, for any internal point, for example I want to find out field at this particular point. We have just seen that because of this charge at any point field is 0, and we have just seen because of this charge field at any point outside is as if the whole charge is at center. You can assume that this whole charge is at center, and at distance r you can directly write. That means to find out field at this particular point, I need to just get the total charge inside. Field at this particular point will be only due to the charge enclosed up to here, because this charge won't have any field inside, just now we have seen. So outer charges won't have field inside. Field at this particular point, or any point outside is due to the charge enclosed. So if I can calculate this charge, I can find out field. Now I hope this point is clear that we are using here. So if volume charge density here is rho, that is nothing but total charge q divided by 4 by 3 pi r cube, right. What would be this charge? Right. Let the radius of a sphere is capital R, and so radius of a sphere is capital R, and we want to find out field at distance small r, right. Here I have taken a small part whose thickness is dr, right. So to get total charge up to r, because this thickness is very small, right. So total charge up to r. So any element you consider inside, somewhere here you consider element. Let the charge on this one is dq, So what I need to do is, I need to write field E is equal to, because of this element at some distance small r, field produced k, charge on the element divided by r square, right. Now r is a fixed point where I need to find out field. So if I add the contribution of all shells, then I will get the total field. So to get total field I need to integrate. So E is equal to, here if you see this is K R square dq integration, and from here to here if charge, if I assume this charge to be capital Q, so that it will become easy to write, right. And if I assume that this total charge, what we are talking about, this total charge is Q, right. So this dq 0 to Q I need to write here, that means I need to just integrate the charge. If I directly ask what is this charge, so this charge is nothing but volume charge density into the volume. Volume here I can write 4 by 3 pi small r cube, volume of this part, volume charge density into volume of this part will give you charge enclosed, right. And we know that this charge is nothing but Q divided by 4 by 3 pi r cube into 4 by 3 pi r cube. This will be the total charge. So integration of this one will give you this one, integration of dq will give you this, right. So when you substitute this value here, integration, the complete value 4 by 3 pi, 4 by 3 pi will get cancelled out. So we are left with K R square Q divided by R cube, Q divided by R cube into small r cube divided by R square. If we simplify, then we will get KQ R cube, this R square and this R cube, sorry, this is extra R I have written, this is extra R I have written, right. I hope you are understanding. So this whole thing appears here, this R square is this R square, when this R square gets cancelled out by R cube, only R small r is left. Look at the expression. This is the first time we are getting field proportional to R. As R increases, field increases. So as you move from center to surface, field keep increasing. Exactly at center, substitute R is equal to 0, exactly at center it will be 0. But as R increases, small r increases, you reach to the surface, small r will be equal to capital R, the field will be highest at that point, right. So expression of field is KQ small r divided by R cube. I can also write this in terms of density. If I multiply and divide by 4 by 3 pi, in the same expression I am doing that, 4 by 3 pi, right. So this gets converted into, this you can see, this gets converted into rho, and K is nothing but 1 upon 4 pi. So 1 upon 4 pi epsilon naught, 4 pi will get cancelled out. This can also be written as rho density divided by 3 epsilon naught, Q upon 4 by 3 pi r cube. This whole thing gets converted into density from this expression, right. 1 r is left. Now as this K is 1 upon 4 pi epsilon naught, this 4 pi and this 4 pi will get cancelled out, only thing left is epsilon naught and this 3, so 3 epsilon naught, right. So for any point inside, in the case of uniform distribution, we know how field varies. Now let us erase this one. One more point, even if the distribution is something like rho is equal to rho naught r, or rho is equal to rho naught r square. Here we have taken the example rho is equal to rho naught. It was uniform distribution, right. If distribution is something like this, again the procedure is same. You have to integrate the charge first. Now you cannot write this rho is equal to q upon 4 pi r cube. Now in place of that rho, if you write rho naught r, then one extra r will come and the integration will be something different. So for all such type of situation, you have to first integrate to get the total charge enclosed, and that total charge you can substitute, just a moment, that total charge you can substitute, this whole total charge you can substitute in the expression to get the field variation, right. So let us first erase all. So I want to find out field at distance r, then we have just seen the procedure and we got this result. So k, this can also be written as, here the total charge is say q distributed over whole volume. So charge is distributed over volume uniformly. Right, it's easy to remember this way, k q small r divided by r cube, or we can also write in terms of density. Just now we have seen that this can be written in terms of density rho r upon 3 epsilon naught, very important expression. So remember this one. Now for outside point, again, as this distribution is highly symmetric, for outside point I can assume that whole charge is distributed at center, and for any outside point I can directly write kq by small r square. So for any point outside we can write kq divided by r square. So now you can see that field inside varying with r linearly, e to the power 1 r to the power 1 linear variation. So inside field is varying linearly, so it is increasing linearly, but as you go outside you can see that here 1 upon r square is coming. So if I plot the variation, how field is varying as we go from this point towards infinity. So up to the surface it is linearly increasing, and after that it will be decreasing, right. So you can see this variation, field as a function of r, small r, where r is the distance from center. So up to surface r is equal to capital R, field is proportional to small r, but once you cross the surface it will be inversely proportional to r square. Right. So this is the way field is varying. I hope this point is clear. Now let us see some example based on motion of charge in field. So we may have uniform field, we may have non-uniform field. As I told yesterday, today we will discuss about uniform and non-uniform field. So when the gap between field lines remains same, then field is said to be uniform. If gap between lines either increasing or decreasing, either increasing or decreasing, either we have this situation or this situation. These are the example of non-uniform field. So, if the gap between line remains same, field is said to be uniform. At each and every point in a space, field will have the same magnitude. So, question here says a uniform field is created between two plates. So, these are the two plates, between two plates uniform field is created. Let the magnitude of field is E naught, that is given, right. So, between two plates there is uniform field vertically downward direction, we need not to consider the effect of gravity, only field is in the space is electric field. Now, what we are doing, we are projecting electron into the field with velocity u. So, as you project the electron into the field, electron as having negative charge will experience force in vertically upward direction, or I can say opposite to the field. F is equal to or E is equal to F by Q naught, right. If I take this charge particle positive, then the direction of force and direction of field both will be same. If I make this charge particle negative, F minus Q naught, then you can see the direction of force and direction of field will be opposite. So, as particle enters into the field, it starts experiencing force in y direction, right. So, it will have only force in y direction, there is no force in x direction. Question says कि with what speed electron comes out of the field if this distance is L. So, very simple question to make you understand what is uniform field and how force acts on the particle and what is the kinematics behind it, right. So, if I ask what is the path followed, what is the path followed by the electron? As there is no horizontal force acting on the particle, the horizontal component of velocity is not going to change. There is a force in y direction, because charge particle is negative opposite to the field, it will experience force. So, what happens, horizontal component to remain same, it starts gaining vertical component also, it starts gaining y component having same x component. So, the path followed, if I drop path followed by electron, it will be something like this. So, at any moment, say somewhere here, it is experiencing force E, where E is the charge on electron, E naught. So, force experienced by charged particle in y direction is E naught, and there is no force in x direction. If I ask what is the acceleration, acceleration in y direction is force divided by mass of electron. So, force is E naught divided by m. As in y direction there is no force, acceleration in y direction will be 0. Sorry, acceleration in x direction, as there is no force in x direction, acceleration in x direction will be 0. This is x, not y. to calculate what is the velocity when it just comes out of the field, it will have one y component and one x component. As there is no force in x direction, the x component will remain unchanged. So, the velocity in x direction will remain u throughout the motion. What about the velocity in y direction? Because of this constant acceleration, velocity in y direction will be increasing, and I can write velocity at any moment v is equal to u plus at. So, velocity in y direction, to get velocity in y direction I need initial velocity in y direction, acceleration in y direction. As particle is projected in x direction, you can see it is not having any component initially in y direction. So, initial velocity in y direction is 0. Acceleration I know that I can substitute here. So, acceleration is e naught divided by m, this is the acceleration. Now, I require the time to get the velocity. So, this is unknown. In this direction its velocity is not changing. So, to cover L distance, how long will it take? So, time taken to cover L distance is L by u, that I can write here. So, the velocity in y direction will become e naught divided by m into L by u. Now, when it is coming out, it will have u in this direction and this value in y direction. If I ask what is the net velocity at this particular point, so velocity at this particular point v is equal to under root vx square plus vy square. You know the value of x, that is u square, you know the value of y, just now you have calculated, e naught by m, e naught divided by m into L by u whole square. So, this is the velocity with which it will come out. Now, if I ask what is the path followed, what is the path followed by particle? So, this path will be parabolic, following parabolic path it will come out. We have learned that when acceleration is constant and particle is projected with velocity which is not along the direction of acceleration, path followed is always parabola. For example, I take particle of mass m and I throw like this with small velocity 1 meter per second or 2 meter per second. As g is always acting in downward direction, the path followed by particle is parabolic. So, as acceleration is constant and particle is not projected along acceleration, the path followed by particle will be parabolic. Same thing happens here, the acceleration is constant and velocity is not along acceleration. If velocity is along acceleration or opposite to acceleration, path followed will be straight line. You throw the particle vertically up, because of the gravitational pull it goes up, its velocity decreases, then it starts coming down. So, path followed is a straight line, but if you project at some angle, then path followed is parabolic. So, path followed here is parabolic. In the situation if g is also given, acceleration due to gravity is given, though that force will be small. If I take that into account, then there will be one more force acting, mg. So, net force here will become e naught minus mg. So, now you have acceleration in y direction, same procedure to find out velocity in that situation, right. So, unless until specified in this situation or all these situations, we do not take the effect of gravity. If nothing is written about gravity, you can assume that there is no effect of gravity, right. So, I hope this example is clear. Field was uniform and path followed by particle was parabolic. Now, let us see next example. So, here a particle is suspended with a string where we have both gravitational field and electric field, you can see that G is also written, right. So, in vertically downward direction we have G, vertically downward direction we have G, and in horizontal direction we have field E. And I want to find out what should be the minimum velocity at the bottommost point so that particle can complete the circle. We have solved similar problem in circular motion chapter where we did not have any external field, any other field, only gravity. So, if you remember, what is the minimum velocity at the bottommost point for it to complete the circle? Value is under root 5 g r, right. But here situation is different. Here we have got additional field. So, due to additional field, what would be the effect? Now, if you remember the procedure here, to complete the circle, condition is there should not be any point where the tension in a string becomes 0. So, at topmost point if it is not 0, then any other point it will not be 0. So, the condition for this value to be minimum, tension here was almost 0, just greater than 0, right. So, particle will follow circle, and for this situation you got this velocity minimum, because chances of tension to become 0 was highest at topmost point. If you take a string and throw it, then chances for a string to become slack is highest at the topmost point, right, where gravity alone can provide required centripetal. So, if gravitational force is not taking help of tension to provide required centripetal, that will be the condition, or that will be minimum condition or critical condition, right. So, in this situation we have to figure out where would be the point where tension can be 0. So, if the resultant force, now you can see that here it will have 1 here you can see because of this field it will have QE force, and because of the gravitational field it will have mg force, right. So, as particle moves this way, these two forces will always act in the same direction. Now, as these two forces acts in the same direction, you can see that chances for tension to become 0 will be maximum where the resultant of these two is coming towards the center, because they alone can provide the required centripetal. So, I need to search a point where the resultant is coming towards the center. So, resultant here you can see resultant somewhere here is away from center. So, it is not possible, this is not the point. Somewhere here if you take, then again the resultant is coming somewhere in this direction, that is not coming towards the center. If I further move and somewhere here you can see the resultant can come in this direction. If you further move, then somewhere here again resultant is not coming towards the center, it is coming somewhere in this direction. So, the point will be somewhere here, right, where resultant can come towards the center, right, as it is given that QE is equal to mg. QE, this force is equal to this force. If this force is equal to this force, resultant can come towards the center when this angle is 45. This force is equal to this force, then resultant can be towards the center when this string is making 45. So I got the point where chances of tension to become 0 is highest. So if I project the particle with velocity in such a way so that here if it is having at least the velocity, so that these two can together provide the required centripetal, it can easily complete the circle. Obviously if I project particle with the velocity higher than this one, then particle will reach to this particular point and then the tension in the string will be non-zero. I need a minimum velocity, right. So if I am projecting with minimum velocity, condition that the tension in the string will be 0, right. I am drawing diagram, this is a string. This blue line is representing string, right. So Q is equal to mg, I am directly writing mg here, Q E is equal to mg and this is mg only. Now I hope concept and approach both are clear. Let us see how to write the equation. So approach is clear. Now let us see how to solve the problem. If I ask how many unknowns are there, I do not know velocity at this point, I do not know velocity at this particular point. Let the velocity be v. So I do not know this v min, I do not know v. So there are two unknowns. So I need to write two equations. First equation is the condition. Just now we have discussed condition. So if I draw free body diagram at this point, then one force is tension, right. So tension plus mg cos 45, mg cos 45 directly I am writing mg by root 2 plus the component of QE in this direction, that is again QE is equal to mg by root 2 must be equal to mv square by capital R or L, whatever is the length given, R, let us write R, right. This is the first equation, right, force equation. Now we want this to be minimum. For this to be minimum, this will be minimum. For this to be minimum, these two are constant. This to be minimum, this value has to be 0, critical condition, right. As I want this minimum, if we are projecting with minimum velocity, then here also it will reach to minimum velocity. For that condition is tension to be 0. This is first equation. I can further simplify, I can write this as root 2 mg R is equal to mv square, right, and this m and m will get cancelled out. So that means v square is equal to under root gr. How I can reach from this point to this point? As there is no external agent involved, once I have given the energy, I am not doing any work. This tension is also not doing any work, because tension is always perpendicular to the velocity. Tension is always perpendicular to velocity. Work done by this tension is 0. So I can use work energy theorem. Work done by external, no external force, I just release, after that I do not apply any force, plus work done by tension is equal to change in kinetic energy plus change in potential energy. I can also write work done by this electric field, this side, work done by field plus work done by field. Now and here I am writing change in potential energy associated with gravity. So there is no external force, this quantity will be 0. There is no work done by tension, this quantity will be 0. So these two will be 0. What is the work done by field? Force into displacement. Now when particle moves from here to here, the displacement it suffers along the direction of field is opposite to the field, this much. Particle moves from here to here along the field, displacement is this much. So displacement is r, this distance, this is the displacement, right. As it comes from here to here, in x direction displacement becomes 0. Then as it further moves in x direction, this is the displacement, right. So work done by field, this I am writing, field is q into E, displacement is r by root 2, angle is 45, r by root 2 with minus sign, because force is in this direction, displacement at this time up to this time is in this direction, so minus sign, right, is equal to change in kinetic energy, final minus initial, half m v square minus half m v min square, final minus initial plus change in gravitational potential energy, again final minus initial. Finally particle, if I take this as reference, if I take this line as a reference, initial potential energy of particle was 0 and finally particle reaches to this side, from this level particle reaches to this side. So this is r and this is again r, if this total is r, this distance will be r by root 2. So r plus r by root 2 is the displacement, right. So final potential energy is mg, position is r plus r by root 2 minus initial potential energy is 0. Now see number of unknown and number of equation. So this is the first equation we made from Newton's law of motion, Newton's law of motion, we made first equation, and the second equation from work energy, this is the second equation, and the number of unknown we have, we do not know value of v, we do not know value of v and we do not know value of v min. So there are two equation, two unknown, you can solve, there are two equation and two unknown, we can solve and we can find out the value of v min, right. So I hope approach is clear. So I have taken example of circular motion where uniform field was applied, and what you used to do for a suspended particle when only gravitational field was there, and what you are supposed to do when both the fields are applied. I hope this is clear, right. Now let us take another example. So charge is uniformly distributed over a sphere and then a cavity is created, cavity of radius r by 2 is created, right. And what we are doing, we are releasing charge particle minus q from the center, right. So from a sphere of density, charge density rho, if you remove some part, the density of the remaining part will remain rho only. From a sphere, if you remove some part, then the density will remain same. It is the total charge on the system that will get affected, but the density will remain same. So even after removing some part, the density of the remaining part will be rho only. And here what we are doing, we are releasing minus q from the center of cavity, find the velocity with which particle strike the center of sphere. So, particle will move and it will strike the center of sphere, and with what velocity it will strike, that we need to find out, calculate the velocity. So, most frequently asked question, right. So, how to approach? So, one thing is clear, to get the motion of this particle I need to have idea about the field inside. So, if I know the field inside, then only I can predict the motion of this particle. So, what is the field inside the cavity? Okay, that we need to find out first. To get the field inside, let us use another slide, then we will come back to this one. So, ultimately I can say that this system is nothing but, from whole sphere, if you remove this sphere, then you will get this, right. So, from this whole sphere, if you remove this one, then you will get this one. And if I want to find out the field, say at this particular point, somewhere here, let us call it point P, and that P point will be somewhere here, and here P point will be somewhere here, right. And we know, just now we have derived the result, like if we have a uniform charge sphere, if we have uniform charge solid sphere, then field at distance r, if the radius of this one is capital R. One way we can write in terms of the total charge. So, if total charge is q, then I can write kq small r divided by r cube. This is one way of writing. Another way of writing is in terms of density, that is rho r upon 3 epsilon naught. Just now we have seen rho r by 3 epsilon naught, right. If I want this one in vector form, this is magnitude, rho r upon 3 epsilon naught is the magnitude. If I want this in vector form, if charge is positively distributed, like if charge is uniformly distributed over the whole volume, then at this particular point field will be radially outward. For all these points at distance r, radially outward, right. So, the direction of field will be same as the direction of r, whatever be the direction of r, same as the direction of field. So, to write this in vector form, I can use this expression, whatever is the direction of r, same is the direction of field. So, instead of going by charge, because every system will have different charge, but every system will have same density. So, it would be better if we write in terms of density, right. That is why I have written in terms of density, rho r upon 3 epsilon naught r vector, very important format, remember this one. So, I can say here, let this point is some r dash from center of this big sphere, and this will be r double dash, right. And if I draw here, then one will be like this, another will be like this. I hope you are understanding. This is r prime and this is r double prime, okay. What is the field at this point because of this whole thing? I can use this expression, rho r upon 3 epsilon naught. So, for this situation I will replace r by r dash, and to get for this expression I will replace this r by r double dash. So, this will create field at this point, this will create field at this point. If I subtract the field created by this at this point from the field created by this at that particular point, then I will get the net field at this particular point. That is the approach, right. So, let us use rho r upon 3 epsilon naught. Let us call the field as E prime. So, E prime is equal to rho r prime vector upon 3 epsilon naught, and here this is E double prime, that is rho r double prime upon 3 epsilon naught. So, from this big one I need to subtract this one to get this arrangement. That means net field at this particular point is nothing but E prime vector minus E double prime vector. So, I will substitute both the values there. You can see that rho upon 3 epsilon naught, rho upon 3 epsilon naught, both are same. Okay, let us first write rho upon 3 epsilon naught r prime vector minus rho upon 3 epsilon naught r double prime vector. Now, these two terms are same, I can take them out. So, I can write rho upon 3 epsilon naught r prime minus r double prime. Now, look at this one, subtraction of two vector, subtraction of two vector can be written addition of two vector with the reverse direction of second one. I will reverse the direction of second one and I can write this way. Right. In the diagram, if you look at this, I need to reverse. So, this we are going to reverse. Now, this will be the direction of minus r double prime, and from triangle law we know this vector plus this vector is equal to this vector. From triangle law we know, or polygon law we know, that this vector plus this vector is equal to this vector. A vector plus B vector, A vector plus B vector will give you C vector, this is C vector. Line joining tail of first vector to the head of the last vector, line joining tail of first vector to the head of last vector, this plus this will be equal to this one. And in this situation, if I take this as x axis, if I just take this as x axis, if I take this as x axis, this distance will be r by 2, and in vector form if I want to write will be I cap if this is x axis. I assume this to be x axis and this to be y axis. So, if in vector form I want to write, ij form I want to write, I can write r by 2 I cap. So, here you can see that this can be written rho by 3 epsilon naught, this whole thing is r by 2 I cap. This is the net field. You can take this point P anywhere inside the cavity, you will always get the same result. I have taken a journal point where this is r dash and this is r double dash. For this journal point I am getting this result, irrespective of the point wherever I take, I will always get this result inside the cavity. That means that inside the cavity, you can see inside the cavity field is always along x axis. In this situation field is always along x axis and it will have the same magnitude, rho upon 3 epsilon naught capital R by 2. So everywhere field will be same and it will have this magnitude. Direction always along x axis irrespective of the point you take. Somewhere here if you take, then this vector plus this vector will again give you this vector. Somewhere here you take, this vector plus this vector will give you again this vector. So everywhere you are going to get same magnitude and the same direction. That means inside cavity field will be uniform, right. Now in place r by 2, in place of r by 2, I can have the cavity of some different size. Here in question it is given that cavity of radius r by 2 is created. So we may have a situation where the cavity is created with of lesser radius and at different location, it might be at r by 4, r by 3 or something from the center of the sphere. Then whatever be the gap between center of cavity and center of sphere, that distance is coming here. That means depending on this gap you will get different magnitude. So if I create a hypothetical situation where cavity can be moved, I can drag the cavity in. As cavity start coming in, the gap between these two centers start reducing and this value start reducing, this whole value will reduce and the field when these two will match will become 0. So the value inside the cavity depends on the gap between center, right, and the magnitude is given by rho upon 3 epsilon naught gap between the cavity. Here I will write so that you can remember gap between cavity. Sorry, gap between center of cavity and center of sphere. Cavity and center of sphere. Right. I hope this one is clear. Let us see one animation to understand what I am saying. So this is a sphere and cavity, we have taken this distance r by 2, right. Now what I am doing, I am taking hypothetical situation where I am just moving cavity. So as I move cavity, this gap reduces. This is representing the electric field, this red one is representing the electric field. So electric field inside will be uniform, right. Right now electric field inside will be something like this, uniform everywhere, and the value we have just calculated, the value was rho r by 3 epsilon naught, where this was the gap. In this situation it is r by 2, right. So everywhere field will be uniform given by this expression. Now what I want to say is, as I move the cavity, this center starts moving towards the center of a sphere, this gap start reducing. As this gap start reducing, the magnitude keep decreasing. So this is representing the electric field and the length represents the magnitude, right. Now see, so you can see as cavity is coming in, the magnitude of the field is reducing and finally when they overlap it will become 0. So when cavity center is exactly same as the center of a sphere, this value will become 0. Let us see once again. So cavity is getting in, gap is reducing, the vector is also reducing and becoming 0, perfectly 0 when it is inside, right. So I hope this example magnitude and everything is clear. Now let us get back to the problem we started. So now we have the magnitude of the field inside. So field is something like this. So if this is the way field is there, you release the charged particle, it will experience the force opposite to the field and strike the cavity somewhere here. Strike the cavity somewhere here. Question is what is the velocity with which particle strikes, right. So if I get acceleration, I will get the velocity. What is the acceleration? Acceleration is force divided by mass. Acceleration is force divided by mass. Force is what? Q into E. So Q into electric field. What is the electric field? Just now we have seen, that is rho upon 3 epsilon naught into r by 2. That is the field due to this charge. Right. So this value I can substitute here. I need to divide this by mass, right. Now I need to find out the velocity with which it hits the wall of cavity. So particle will move opposite to the field and will hit the wall of cavity somewhere here, right. So somewhere here finally it will come, moving like this. So as acceleration is constant, I can use 3 motion equation: v is equal to u plus at, s is equal to ut plus half at square, v square is equal to u square plus 2as. Out of these, the most suitable one is v square is equal to u square plus 2as, because we know the displacement. Displacement is r by 2, right. So v square is equal to u square plus 2as. It is released, so this value will be 0. So v square is equal to 2 into a is equal to QE by m into displacement. This is displacement, displacement is r by 2, right. So simplify this one, this will go on other side and you will get, so square will go on other side and then you will get right. So today we have discussed how the particle will move inside the field, and we talk about the field due to various distribution like hollow sphere, solid sphere. So till now we have covered particle, ring, disc, sheet, hollow sphere, solid sphere. So remember all the expression what we have derived, because if you remember then you can save time during exam. You can directly write the expression and solve problem. So today I have taken all the example of uniform field. Tomorrow I will take example related to non-uniform field, right. So I hope you all will be downloading the assignment and solving, right. So if you immediately solve the assignment given to the concept, then you can check the application part whether you are understanding or not, right, and immediately you can post your doubt related to whatever question given in the assignment or whatever doubt you have in the theory part I am discussing, right. I am trying my level best to give you the idea about how the type of question comes or how many types of question comes in the exam, right. So this is the question what I have discussed today. It has been asked so many times, right. So in the class you will get some idea ki what is the level of question asked in JEE Advanced and Mains. After solving the assignment you will be having idea that what you have understood during the class. There might be some problem related to the theory, you can immediately go through your textbook. I consider S.C. Verma as the best book for basic theory. So, basic theory you will get from S.C. Verma, and you can understand what I am teaching in the class. If even then you do not understand anything, then you can post your doubt and I will try to answer them. In the last class, one student posted doubt that why the component of field in y direction is 0. So, in the whole class I discussed so many slides, right. If you don't be specific, then I won't be knowing what you were asking. So, better whatever I am writing, look at this one. So, for example, this is the main heading, and main heading I discuss something. So, you mention your doubt related to the main heading. In that particular slide where main heading was this one, I did not understand this particular part, then I can easily cover it up, right. If you do not mention anything, I might be confused what or specifically at what slide you had doubt, right. So, you can post your doubt again being specific related to the slide and the related to the subtopic, right. I hope you enjoyed today's class. Thank you.